Hi everybody and welcome to a new video in the Deep Learning Audio Application from Design to Deployment series. This time it's super exciting because we are at a moment where we need to start making predictions with our speech recognition system. And so for that we're going to build a class that's going to be called Keyword Spotting Service that's going to be responsible for, as I said, making inferences with the model that we trained in the previous video. So as a first step here, we need to create a new Python file. And not surprisingly, we'll call this Keyword Spotting Service. Here we go. Cool. So now we need to build this Keyword Spotting Service class. And so I'll write it down here. So Keyword Spotting Service. Now, this class is going to be a singleton. So if you're not familiar with a singleton design pattern, what this is basically a class that can only have one instance in a program. So you may be wondering, but why are we using a singleton? Well, it turns out that we are going to use the keyword spotting service in our Flask API in an endpoint, and we want to only load a keyword spotting service like once, right? Because we just need an instance. So in order to ensure that we're going to have only one instance, we want to just like make this class a singleton. So let's get into it. So here we have the keyword spotting service class. So here we'll write down three different class variables. So the first one is going to be called model, and this is just the TensorFlow model that we trained in the last video. So for the time being, we'll set it to known, but then when we instantiate the class for the first time, we're going to actually load the TensorFlow model. So the next class variable is called mappings, and if you guys have followed so far, you know that we need to go into our data JSON file, and here we are gonna get this mappings list here. And so, as you've probably guessed, this mappings is just the mappings between our keywords and like the numbers of or indexes that our network uses for making predictions. And then we need another private class variable that we'll call instance. And again, we'll set instance to known, and instance is the keyword spotting service instance itself. Now, why do we need this instance variable? Well, because this is one of the tricks that we are going to be using for implementing this class as a singleton. So why do we do this? Well, because Python, differently from other programming languages like Java, for example, doesn't enforce a singleton. So there's really no native way of like creating a singleton. So we have to create like a way like of enforcing that. And this instance variable is going to help us like in that deed. Okay, so now before jumping into the methods for the keyword spotting service class, we want to create a factory function that's going to be responsible for instantiating a keyword spotting service. Okay, so we'll call this keyword spotting service, right? And so here, what's important is to ensure that we only have one instance of KSS, of keyword spotting service. So how do we do this? Well, we use the instance class variable, and we'll use it in this way. So we'll say if keyword spotting service dot instance, and I've just noticed that I mistyped this instance over here, so now it's fine. Okay, so if keyword spotting service dot instance is none, so we haven't created a keyword spotting service instance yet, then what we want to do is actually to instantiate one and to assign it to instance. So we'll just we'll use the keyword spotting service constructor over here, and we'll assign this keyword spotting service instance to the instance variable over there. Good. And now we also need to do another thing here, which is basically getting keyword spotting service dot model and load the model that we've trained last time. So how do we do that? Well, we need keras for that. So let's import keras. So we'll do an import. Let's do import TensorFlow dot keras as keras. And then we can go down here and we'll say keras dot models dot load model, and here we need to pass in the file path to the model that we've trained, and it's this guy over here, this model, sorry for that, this model.h5. So here we'll do a model path, so we need to create this constant, and we can define that over here. And this is equal to model.h5. Good. Okay, so the last thing that we need to do for this factory function is to return the instance. And so we'll return keyword spotting service dot instance. So if you look at this function, like, it's really nice because if you are calling it for the first time, then you'll enter like into like these instructions here, because this condition over here is going to be true. And then you instantiate a new keyword spotting service like instance, and then you assign it to the instance variable, and then you load model. But if keyword spotting service dot instance is not known, so if we already have an instance, then we'll just return the instance itself. So this way, like we have like an elegant way of implementing a singleton class in Python. Good. Okay, so now that we've done this, we need to build the methods that are like important for our keyword spotting service class. So the most important one is going to be the predict, right? So we want to pass a file path that's an audio file, and then we want to get a prediction, so a keyword. So for doing this, we need to perform a bunch of separate tasks. So first of all, we need to extract the MFCCs. And we know that the MFCCs are the inputs that we pass into our neural network. So after we do that, next step, what we want to do is convert to the MFCCs array into for the array. Now we'll look into this like in a couple of minutes, but basically what comes out of like, so when we extract MFCCs from our audio file, we already know that we have a two-dimensional array, and then we need to convert that into a four-dimensional array. As I said, we'll look into the details in a second. And so then we have like the last high-level thing that we need here, which is just make prediction. So we just need to make to do a prediction here. Good. Okay, so let's start with extracting MFCCs. Okay, so we'll create this MFCCs variable, And here, for extracting the MFCCs, we'll need another function, which we'll call preprocess. Well, it's not really a function, it's a method that comes with keyword spotting service. And this method is going to be responsible for extracting the MFCCs starting from a file path or an audio file. So obviously we need to implement this preprocess method. So for the time being, I'm going to create a placeholder here that I'll call def. So I'll define preprocess, and we know that we have a file path argument, and then we'll finish implementing this like once we're done with predict. Okay, so now let's assume we have this MFCC array over here. So if you guys remember, so you should know that the shape of this array is given by the number of segments and the number of coefficients that we extract. And specifically with the settings that we've used when we pre-process the audio dataset, we have 44 segments or snapshots at which we take 13 coefficients. Now, as we said here, we need to convert this 2D array into a 4D array. So what this means is basically we need to arrive at a shape that looks like this. So the first dimension is going to be the number of samples that we want to predict. So why is this important? Well, this is just like the way the predict method from the Keras API works. So it accepts a batch of samples. And so the first dimension here, it just like tells us how many samples we are passing into predict. Then the second and third dimension over here are just equal to the number of segments and number of coefficients. And finally, given we are using a convolutional neural network, we know that we need to pass a three-dimensional input data in there, and the third dimension is the number of channels that we know in our case is equal to 1. Now, if you don't remember like this stuff, so you should go back to my video when like I built like the model. So when we trained and built the model for this like keyword spotting system, and this is like in the last video. Okay, so now we need to convert this array, so from 2D to 4D, and so for doing that, we can use NumPy. So we've already seen like this techniques, I think like in a previous video, but yeah, we are gonna need to use it once again. So we need to create a new axis, a new dimension here, and so we'll do a NumPy np.new axis. Then I'm going to put in 3 dots, and these 3 dots will tell NumPy to consider all the stuff that we already have like in the array, so the number of segments, so the segments and the coefficients. And finally, we need another new axis for the channels, and so I'll do another NumPy.new axis. Now, obviously, the PyCharm is throwing like an error over here because I haven't imported NumPy, so I should fix that. So we'll do here import NumPy as np. Good. So we should be good to go. Nice. So now it's time to make the prediction. So the first thing that we are going to get is a predictions array. And for getting like these predictions, so we need to get the model itself. So this is the Keras model that we've loaded, and then we need to invoke the predict method from the Keras API, and obviously we want to pass in the MFCCs, the 4-dimensional array for MFCCs. And so the output, so the predictions array is going to look something like this. So it's going to be a two-dimensional array, and it's two-dimensional because like it basically like gives us like an internal array for like for as many samples as we have. So if we had passed in like two samples for predictions, we would have like this, like something like this. But in our case, we just have like one sample, so it's going to look something like this. And then like in the like internal array, we are going to have 10 different values that are the scores that our speech recognition system gives to the different keywords, right? So let's assume, for sake of simplicity, that we have like something like this, right? So 0.1, 0.6, 0.1, and then yeah, we have like all the other 7 like values. So let's assume like that this is like the 0.6 is the highest value. Okay, so now what we want to do next is basically isolate or get the index in the array that has the highest score. That's going to be our prediction. So how do we do that? Well, that's quite simple with NumPy. So here we can say that the predicted index is equal to NumPy.argmax of predictions. So this NumPy.argmax function is just going to return the index with the highest score in our array, which in our case is going to be equal to 1, right? Okay, so now we have an index. In our example is 1. So, but we don't want to print an index because it doesn't have like any meaning for us human beings. We actually want to map that index onto the actual keyword. So how do we do that? Well, now you understand why we needed to import or like to define this mappings variable over here, because we want to map this index to the keyword. And so, oops, what have I done? So for doing that, we'll do a predicted keyword that's equal to self.mappings, and then we'll pass in the predicted index. So in our case, so when we are looking up the keywords for our index that's equal to 1 in our example, so we are gonna get back off. So our keyword, predicted keyword, is off in this example over here. Good. Okay, so now the last thing that remains to do is just to return the predicted keyword. And that's it, guys. So we have a very solid predict method now, but we're still missing the pre-process method. We need to implement this. Okay, so here, so for doing this pre-process task, we are going to need to perform a number of different things. So the first one is, obviously, the simplest one is just load the audio file. Then we want to ensure consistency in the audio file length. So we'll see what this means specifically in a second. And then we are just going to extract the MFCCs. Good. Okay, so for loading the audio file, we're going to use this fantastic library that we've used already. That's Librosa. So we'll import Librosa over here. Then we go down here, and then we'll do, oops, here we go. So we'll do signal and sample rate. That's what we get back from librosa.load, and we are going to load this file. Good. Okay, so now we need to ensure that we have the right amount of samples in the signal so that the model that we've trained can accept that and use that to make predictions. Good. So how do we do this? So we'll do a if the length of signal is more than let's just like define a variable or a constant here, number of samples to consider, then we'll just resize this signal, and we'll use this slicing technique over here. So let me just get this number of samples to consider over here. So obviously we haven't defined this yet, so we need to define it, and as it's usually the case, we'll define this like here on the top of our script. And here, the number of samples to consider, you guys should know this, is equal to 22,050 samples, that with our sample rate, it's equal to a 1 second worth of sound. Now, obviously, we need the same amount of samples that we've used also like during training. And this is because we have a convolutional neural network. So when you train a network, the input that you use should have the same shape when you do like inference, like on the same model. Good. Okay. Oh, one thing that I want to like highlight this. So we probably have like the same variable somewhere else, like in our scripts. It's probably called something like samples to consider. Now, I would say like a better way of like having like all of these like constants is to have like an external config file where you put all of your constants, and then you just like draw them from that config file in your current scripts. But I'm not gonna bother like doing that. So like if you guys like want to like improve this is a task that you can do. Okay, so let's get back here. So by doing this, we ensure that if we have like a signal that's like longer than the expected signal, we'll just like resize it so that we'll have like the right amount of samples. Okay, so now we are safe to extract MFCCs, and for doing that, we'll use librosa, obviously. So we'll do librosa.feature.mfcc, and here we'll pass in the signal, and then we need to pass a bunch of other values here that we also used when we did pre-processing on our audio dataset. So I'm going to set them up as arguments here in the pre-process method. And so the first one is number of MFCCs, and we'll default this to 13. Then the frames that, like the window that we use for the fast Fourier transform, and we'll set this equal to 2048 samples, and then the hop length, and this is going to be equal to 512. Okay, so basically here I've used the same values that I've used also when we did pre-processing, when we did pre-process the audio dataset. Okay, so here let me just pass in these values. So number of MFCCs, so the fast Fourier transform window, NFFT, and then the hop length, that's going to be equal to the hop length. Great. Okay, so finally we need to return the MFCCs, but we are going to return the matrix transpose of the MFCCs that have been extracted with librosa. Good. So now we have all of our keyword spotting service class, Singleton class, and it looks like quite nice. So we can do predictions, and for doing predictions we use this like pre-process method. Good. So now what remains to do is to use this keyword spotting service class and see if it works. Okay, so we'll do as usual, if name is equal to main, and then we need to instantiate our keyword spotting service, and for doing that we'll call the keyword spotting service factory function that we've built, and then we'll do predictions. So we'll do KSS dot predict, and here we can pass in the path to an audio file, to a sample audio file that we want to predict. Now here you can see, guys, like in my folder structure, project structure here, that I've created a test folder, and here I've put in a couple of audio samples. So down.wav and left.wav. So these are like samples from the speech dataset that we've used for training the model itself. So I just like need to like pass in like those samples. So we'll do a kss.predict, and here I'll pass in the relative path to down.wav, and here we'll just like put this as keyword 1 is equal to this like instruction, and then we'll do keyword, it's not here. So we'll do keyword 2 that's equal to kss.predict, but not down. We'll do left. Okay, so now to see that everything like is working correctly, we need to print the results, and so we'll say predicted keywords, and we'll pass in keyword 1, and here we hope to see down, and then here we'll pass in keyword 2, and we hope to see left. Good. So I think like it's all ready to go. So hopefully, if I haven't made any mistakes, this should work. So let's try this and see what happens. Okay, so here you see that we are loading so here like we've just loaded the model, and then here we did the prediction and we printed, and so the predicted keywords are down and left as expected. So the model is working correctly. It loads, it makes predictions, and the predictions are also correct, which is a great news. So this is basically it, like for the keyword spotting service. So next time, what we're going to do is basically take this keyword spotting service, and we're going to implement our Flask API, where keyword spotting service is going to be called from an endpoint. So stay tuned like for the next video, and I hope you've enjoyed this video. And if this is the case, you should definitely like consider subscribing if you haven't done so, and hit the notification bell. Now, if you have any questions regarding like what we've done, what we've covered in this video, please leave them in the comment section below. And I guess I'll see you next time. Cheers.